Okay, thank you very much. Hi to everybody. So, yes, can you hear me and everything works well?
Yeah,
Okay. So, I would like to start with a short, maybe a short recap of what we have seen yesterday. Indeed, most of the material that I was presenting was probably, say, rather new to you. And the first, again, so if I go back to the main outline of what I wanted to talk to you during this week, again, yesterday I essentially talked about this part, and I first show you that these fermions were, I mean, in some cases at least, were directly connected to random matrices. And one example that I discussed in detail, or I tried to discuss in detail, was the case of basically this one, which was the case of fermions, non-interacting fermions in a quadratic potential. And the first part of the lecture was devoted to showing this quite nice identity, which is here, and which, as it is written here, maps the positions of the fermions, in this case, the xi's, to the eigenvalues of the random matrices belonging to the so-called Gaussian unitary ensemble. Okay, so that means here that this was the exponent beta equals 2 that we had encountered before. And
Uh,
again, this is, sorry,
yeah, I had a question actually.
okay,
So in this case, like we said, we chose a harmonic potential, and we arrived at this um, uh, like form for the probability of wave function. So we already knew that this. We have already seen this is an eigenvalue distribution of GU ensemble. But suppose we didn't know, and we arrived at such an expression. How do we know that it's from a random matrix model? That it corresponds
yeah.
to a random matrix model.
Okay, that's a good question. I mean, I believe that it's a bit fortuitous at this stage. I mean, in the sense that there is no indication before arriving at that result that there is a random matrix behind this model, indeed. So, indeed, there is no signature of random matrices before that. In fact, one of the things is that you see we only have the eigenvalues, but we don't have the eigenvectors. The eigenvectors are not there. Okay, so in one sense, if you want at the matrix level, I think the mapping is a bit incomplete. But the mapping is really at the level of the eigenvalues, and in that sense, I think it cannot really be anticipated, except at a very vague level that we have seen before, that there is this level repulsion in the random matrix models. And okay, it's not that we had already seen that there was a kind of repulsion which is a bit akin to what fermions do experience, but there is no indication of that. I mean, if you don't know, if you haven't seen before this joint distribution, it's basically impossible to guess it, I would
So
mention.
exactly, my point was towards this repulsion which we are saying. So for example, if we consider any other potential and we find some sort of level repulsion, can we safely say that or predict that it might be a random matrix model?
No. I mean, so there are some fermions models that are connected to random matrices, but in general, if you take a generic potential V of X, there won't be any matrix model behind it. Okay, so that's the fact that there is a one-to-one mapping is really, I mean, concerns a very few examples, and one of them, the prototype of them, is this one.
Like my precise question is like if we observe any sort of level repulsion in our distribution for eigenvalues, can
Mhm.
we say that it might be related to a random matrix model?
I think it's not true. I mean, I think that one thing which is true probably is that if you observe such a repulsion, it is very likely that you will have a kind of determinantal process in the way that I defined it in the previous lectures. But random matrices is only one kind of determinant. I mean, random matrices for GUE, but it's clearly not enough. It's really
Okay.
not enough.
Yeah, hi. In the similar spirit, like I have one question. So
Mhm.
for the GOE, is it possible to realize some ground state of some correlated fermions, maybe some
Yeah,
fractional?
so that's a good question. So in general, in fact, you can look at generic beta here, and you are asking about beta equals 1. So indeed, this might be realized by the ground state of a quantum model, namely fermions in harmonic potentials, but with interactions, and with very specific interactions, which should be of the form of 1 over x squared. So if you have an interaction between the fermions, which is of the form like in the Calogero-Sutherland model, right? 1 over xi minus xj squared, then this will be connected to some beta ensemble.
Okay. I mean, typically we can make an ansatz for like ground states of this many body Hamiltonians in some J-Stro form.
Yeah.
That might give clue that like there will be some
So
connection.
okay, so we recently actually wrote a quite big paper along these lines. I can give you the, I mean, if you write to me, I will give you the references where we really try to make this in a quite exhaustive way.
Okay. Thank you very
Yeah.
much.
Gregory, I had a very similar question as what Hari asked. So beta equal to 2 ensemble came because you are looking at quantum mechanical systems. But you could look at classical system, for example, interacting particle with like the Lieb lineager with absorbing boundary conditions. There you would have similar beta on that with this like alternating sign for the permutations, which so in that case you would probably guess you would get the beta equal to 1. Is that like, so my question is, for example, Lieb lineager gas model in a harmonic potential, would that give you a classical beta equal to 1?
I'm not so sure actually. What I can say is that if you take the Lieb lineager model, so bosons with the Lieb lineager interactions in a quadratic potential, what you will eventually get, at least at the quantum level, say again in the very strong repulsive limit, so the Tonks limit, you will get these fermions essentially. At the classical level, I don't know. I must say, I
So
don't
like
know.
if you have vicious Walker, so it's you get if you do the
Yeah, I will come to that later. So indeed, with
Ah.
vicious walkers, I think I will discuss this a bit later. Indeed, with vicious walkers, you can have beta equals 1.
Right. Okay.
Yeah. So that's indeed related to that. Yes, that's true.
Okay. Thanks.
Okay, so maybe I will just end up with that. I mean, at least on this model, the thing that I wanted to say is that is about the origin of this term here. If you remember well, I mean, in the context of random matrices, this actually came up because we were computing a Jacobian. So that was coming from a kind of rather mathematical object, namely this Jacobian. Here, really, it comes from the exclusion principle, okay? Because we have fermions, then typically they don't want to sit close to each other, and these terms, in this case, really arises because of the Fermi exclusion principle. So that was the first thing that I showed you, right? So this direct mapping between fermions and the Gaussian unitary ensemble. And then I discussed very important concepts, which is the fact that in this model, what happens is that if you look at the density, which is in blue here, the density will have a finite support. And for the GUE or for the harmonic for fermions in a harmonic potentials, this is just given by the Wigner summer circle. Okay. And this allows to define essentially two distinct regions, two distinct scaling regions. I mean, this distinction, of course, only makes sense in the large n limit. One, which is a region which we usually call the bulk, and which is basically in the center, I mean, close to the center of the trap and not too far from the edges. And in that case, the physics is described by a correlation kernel, which has a typical form, namely the sign kernel. I will just come back to that in a minute. And the other regime, which is also very interesting, and in fact, in view of recent progress in random matrices, This is somewhat more interesting from my point of view, but this is these are this is the edge regime. And the next thing that I discussed from a general point of view, in fact, from fermions, is the fact that we have what we call a determinantal point process, and that's a quite important families of random points, which are such that if you want to compute any correlation function of that type, so how is it defined here? Well, basically this is just defined by, so psi 0 squared is the endpoint joint density, if you want. So that's the density, the probability density function for the positions of the n fermions. And then you can imagine that you are integrated, you want to integrate over a given set of positions, say from small n plus 1 to capital N, and you will be left with correlation functions, small n point correlation functions. Now, the very nice thing with this process is, in the context of fermions, is that these correlation functions, they can be written in terms of a small n by small n determinant. So small n is here, and the only data that you have to know is the kernel, and that's really the central object in all this this problem here. And this kernel is actually can be built explicitly from the single particle eigenfunctions as it is here. Okay, so that means that again you are looking at the ground state. So the sum here just go from m equals 1 to n. So that's this picture, okay, that I had before. So you are just populating the n first levels because you are looking at the ground states. So the sum here stops at n, sorry. And then this kernel is simply given by this quantity. Now, given the importance of the kernel, and because we are usually interested in what happens in the limit of a large number of fermions, you want to understand, it's important to understand the form of the kernel in the large n limit. And what I discussed with you is first the limit in the bulk, where one has the sign kernel, which is quite well known in RMT and beyond. It actually describes the correlations on a quite short scales and deep in the center. While if you look at the edge, you get a different kernel, and this is this by now rather famous Airy kernel, from which one can construct, for instance, the Tracy-Widom distributions, and that's what I ended up with last time. Now, this is all nice, but this is of course at t equals 0, okay? And it's clear that in many cases, in particular in experiments, people are actually working at finite temperature. And what you would like to understand is what happens precisely at finite temperature. So that's what I want to discuss today. Okay. So let's start with what basically quantum mechanics tells us at finite temperature, and let's try to. The first object that we would like to write is the joint probability distribution for the particles, for the position of the particles, but at finite temperature. Okay, so that will be the first object that I want to look at, and this is given. This is basically given by quantum mechanics. And in particular, this is given by the density matrix, right? So let's have a look at how it is. Okay, so the question and the object that I want to write is really this this joint distribution x1, x2, xn at finite temperature. So quantum mechanics tells me that this is the diagonal part of the density matrix operator. So rho hat here is just 1 over the partition function exponential of minus beta h hat. So that's the n particle Hamiltonian. Okay, and what I really need to do here is just to compute the this matrix element. Okay. Now you see the problem. I mean, or the problem. Say when you will then, so you will insert. So what the way to do is simply to insert now this operator here, here, and then you will expand this. You will then expand this operator in the basis of the eigenfunctions of this operator and particular eigenfunctions. But do you see that now the situation becomes a little bit more complicated than it was before, because maybe I can just illustrate this on this. Sorry. Okay. Well, let's do it. So let's just do it as we did before. So if I just look at my potential and the energy levels that I had, so this is typically my V of x. Okay, and well, we have seen, no, that we have the energy levels. I mean, that we all know from very standard courses. So you have these levels here, and what happens in the ground state, as we know, is that okay, at t equals 0, it's relatively simple, right? Because you just populate all these guys like that up to the level n, say. Okay, so you have the first level, the second level, etc., etc. But of course, now it might be that if you are at finite temperature, you will have all kinds of states, which of course involve any n states that you can construct from these various guys. So typically, I mean, you might have a state where, well, I mean, for instance, this guy will be say empty. Oops, sorry. Okay, and it will go upstairs. Okay, so that would be a kind of excited state. But then similarly, you could have this guy that goes upstairs, etc. So that means that I will have all the I will need to consider all the possible excited states that I can construct from the single particle Hamiltonian eigenstates. So in other words, that means that if I write this, let me write this formally, what this guy is. I mean, this will be a collection of Slater determinants squared that you can construct from any nuplets. Okay, so let me write this formula and then I will discuss it. Okay, so this P joint is a quite complicated object now, but physically it's relatively simple to understand. So there is, okay, some normalization factor that I write it in this way, and then I have a sum. So what I'm saying is that I select a set of states which are labeled by K1, K2, Kn. So that will be, for instance, K1, K2, K3, and then Kn would be this guy, etc. So any combination of n states, and from them I will construct the Slater determinant. Okay, so that's Slater determinant associated to these states. And then, of course, because we are in quantum mechanics, what we need to consider is the modulus square of this. And now, of course, each of these configuration now has to be weighted by the Boltzmann weight, which is simply exponential of minus beta epsilon K1 epsilon Kn. Okay, the formula is a bit ugly, but I think physically it's relatively clear what it is. I will not play too much with it. Maybe I should be a little bit more precise because, of course, they have to be different. So, and They are ordered actually this way. Anyway, these are fermions, okay, so they cannot occupy the same state. So this formula is exact, and then in principle, we would like to understand how it does behave for large n, okay? Well, what can I say? What can I do with it? Well, obviously, the formula is rather complicated, and I just wrote it, but I will not do so much with that, okay? It's still possible to do things, but I will not comment on that. The main thing that you need to see here is that instead of having just a product of two determinants, as we had before for determinantal point process, we now have an infinite sum of product of Slater determinants. And the result of that is that, well, first you lose the connection to GUE. I mean, of course, there is no matrix behind it. I mean, at least no easy model behind it. But more importantly than that, it turns out that this process is not determinantal anymore. So that means that all the nice tools that we had before have become useless.
Gregory,
yeah,
I just get confused with something very elementary. So
yes,
these are all non-interacting fermions and at finite temperature. So where is the Fermi-Dirac statistics coming into it?
So here, no, it's not clear at all actually. And in fact, okay, sorry, I just realized that there was a small mistake in my formula. Yeah, so at this stage, it's not, I mean, the Fermi-Dirac statistics, in fact, is not very apparent. And the reason for that, and this is somewhat related to the difficulty that we are facing here, is that in this formula, n is fixed. So that means that we are actually working in the canonical ensemble.
I see, okay.
Okay, and but that's actually...
Then you can't do fugacity, deciding the fugacity with the standard way that we do. Exactly.
So that's actually the thing is that the reason, in fact, the reason why say the problem is difficult is that precisely we are working in the canonical, but it turns out that it's much more, and we know from quantum mechanics of quantum statistics in general, we know that it's much more convenient to work in the grand canonical ensemble. And we expect that things, or we may hope that things will get simpler in the grand canonical ensemble. And then in a large n limit, or in the limit of large number of fermions, one may hope that that the properties, the local correlations, will be the same either in the canonical or in the grand canonical ensemble. And that's precisely what we are going to do. So that means that. So at this stage, essentially, that here, this is the end of the story in the canonical ensemble. Okay, so that's sort of what it says is that the canonical ensemble is not, well, it's too complicated in some sense. But this we know somehow. I mean, we already knew. I mean, when you start to study quantum statistics, immediately if you want to define or to compute Bose factor or Fermi factor, well, you have to go. You want to define a chemical potential, and for that you need to go to the grand canonical ensemble.
So then, is the concern that you want to study, for example, different scalings on n, like the edge properties, which may not have this equivalence, and that's why?
Okay, so that's a good question. There is no proof of that, but okay, there are some physics proof of this, but there are no mathematical proof of that at the moment. But it's expected that if you look at what happens locally, so typically if you look at the fluctuations of the rightmost fermions, or if you look at local correlations, for instance, if you look at a kernel, then things should coincide. But if you ask about more general, I mean, or more global properties, then you can even show in some cases that it will not coincide. Okay.
Yeah. Okay. Thanks.
So the trick, as I said, as it was discussed here, is that the trick, is that we now work in the grand canonical ensemble. Where you do not fix anymore the number of particles, but what you fix is, of course, the chemical potential. Mu. Okay, and again, you would expect and you hope that in the large N limit, the things would coincide. Now, the remarkable thing is that if you now go to the grand canonical ensemble, this problem becomes determinantal again, and that's why you are now I mean, really you feel much better. Is that in the grand canonical ensemble? So the fermions, so the positions of the fermions are determinantal, or form a determinantal point process. And more than that, it turns out that the kernel is also very, very explicit, and I will just write it explicitly here. And the kernel now is labeled by mu. It's a sum over all the single particle states with all the states. So from k equals 1 to k equals to infinity, it has a very sort of relatively, so this is a form that we recognize, but of course there is something missing here. And what is missing is precisely this factor. So beta is the inverse temperature here. +1. Okay. So beta, be careful. Beta is the inverse temperature here. So maybe I should, this is not the beta from RMT. So beta is 1 over kBT. And of course, you see that here, what you have is the Fermi factor. Okay. So now you start to recognize. You feel that you still recover a little bit what you know from standard quantum mechanics. The first observation is that you see indeed in the limit of 0 temperature, this Fermi factor is really becoming a step function, and basically that means that this will be 0 for epsilon k larger than mu and 1 below mu being in this case just the Fermi level, and that means that the sum that you have here will just be cut. So instead of going to infinity, it will be stopped at mu. Okay, or say at k such that epsilon k is equal to mu, and therefore in this case you would just recover the standard. The kernel that we had before, right? So that's you will immediately recover this guy. Okay, so
hi, I have two quick questions. One is, I missed the point. Like, why is it difficult to compute it in the canonical ensemble? Can we not do some fugacity expansion or something? Why is it so difficult?
Well, see, difficult mean in the sense that I'm really interested in. I want to understand what happens in large N limit. I want to have a detailed analysis of the kernel and the correlations in this model. And I'm saying it's complicated. It's much more complicated than what happened before, because we lose this determinantal structure. Okay, so you cannot use all this nice machinery that I explained to you yesterday, where you have a determinantal point process, and from which you can basically compute whatever you want, gaps, probabilities, etc. You can still do things, as you said, and people, of course, have studied, I mean, at least tried to study these kind of problems. But for instance, if you want to say something about the edge properties, this is very difficult in this ensemble. I'm not saying it's impossible, and in fact, there are, in some cases, that there have been recently some works, in fact, mainly by mathematicians, to try to understand these properties directly from the canonical ensemble. But life becomes much nicer and much simpler in the grand canonical one because of these properties.
Okay. I mean, one can do this so-called this Levitov-Lesovic formulas in fermion counting statistics in transport processes, right?
Yes, yes.
So there you can sort of expand in this the fugacity. Is
Right.
it not? Okay.
Yeah, if you want to do some counting statistics in the bulk, you can use these kind of things. Yes, but for instance, as soon as you are facing well, the edge, for instance, is just impossible to get using this kind of formalism. While here you will see that it comes out very nicely.
Okay, thanks.
Okay. Okay.
So Gregory.
Yes, Anupam.
Yeah. So what's the interpretation of the point process for with this kernel? And like in the previous case, you define that you have a joint distribution, which is like joint distribution of in points, and then if you integrate out few degrees of freedom, and then you get the joint distribution of a smaller number of degrees of freedom, but still expressible in terms of determinants. So what's the interpretation in this case?
Yes, so in this case, you really have to basically to come back to imagine that it's a kind of average of correlations average taken over all the possible number of fermions, and which are then weighted by mu essentially. So it's a kind of average of these correlation functions, but where you average over all the possible wave function. Another way of saying it, if you want, another way of saying it is that what you are computing is the generating function of the kernel with respect to n mathematically.
Yes, that's why the mu comes.
Yeah, exactly. Yeah.
Yes,
exactly.
Okay. But in the previous process, you had n degrees of freedom, but here you will not have. So you're saying
Yeah,
that
no, indeed. I mean, in this case,
you have to think it in terms of the mu space, just
yeah, exactly.
Okay.
I think that
And
for
which has
fermions, it's so okay. I think that for fermions, it's really you're right. I mean, conceptually, I think it's like for me, I always I feel more comfortable to view this this grand canonical potential as a kind of trick to treat the large n limit of the canonical with basically with the relation that I'm writing now, the standard one, and that is that you fix n as being equal to that, right? But it's a bit fictitious in some sense. I agree. Sorry. And that's why I sort of prefer to think about it as a kind of trick. I'm more comfortable with this kind of, I mean, with this. And again, saying that what you are actually computing is a generating function of this kn, and in fact, you relate kn and k mu basically by a Cauchy transform, and somehow if you have a nice saddle point, then basically the two ensembles are equivalent.
Yes, I see.
Yeah.
Thank you.
That's a good point. Yeah. Okay. Very good. So I will not tell you how to show that. In fact, okay, again, this property here is known in the fermion community. In fact, there is an old paper by Godin, I mean, from the 60s, who showed this basically as an extension of the Wick theorem at finite temperature. So you can do it in this way. More recently, the probabilists actually have revisited this problem, and there have been lots of papers on this. I mean, there are quite a few activities on determinantal point processes in grand canonical ensembles during the, I mean, at the moment, basically. So it's quite active, relatively active field of research. Now, of course, you would like to understand how this kernel, behave in the large mu limit. Okay, n large. It's not difficult to see that for fermions, n large means mu large. So before doing computations, I think it's nice just to understand what happens when you add temperature and try to understand essentially what can we expect of this kind of picture at finite temperature. Okay, basically what happens to the Wigner semicircle at finite T. So to do that, I think it's nice to just to make and to analyze the various relevant length scales at finite temperatures. So let's have a look at that. So let's come back to this basics. So we have seen basically that at T, at 0 temperature, we have two different scales depending on we are looking at the problem in the bulk or at the edge. Okay, this we have seen that. In the bulk, if I look at the typical length scale in the context of fermions, this is of order 1 over square root of n. Okay, again, my Wigner semicircle here in the fermion language is of order square root of n, and I have n fermions on that interval. So square root of n divided by n gives you this 1 over square root of n. Now, if you are at the edge, that was this scale. Okay, let's call it L edge. This is what I used to call Wn before. In the case of the harmonic potential, okay, I'm still having the harmonic potential in mind. And this is the Tracy-Widom regime. So in the language of random matrices, you remember for random matrices, this is of the order n to the power minus 2/3, but there is the square root of n difference for fermions. And I already mentioned for you yesterday that the scale is actually n to the power minus 1/6. Okay. So, and I would like to understand how this behavior, how these regimes are modified when I add temperature. So when we know that when you add temperature, there is a new length scale that enters into the problem, which is the de Broglie wavelength. And typically, this is the extension of this is the typical extension of the wave function due to temperature. And this we know under the Broglie wavelength. I mean, this is a standard length that we have learned at school. That's just h divided, say, by square root of, okay, just square root of 2 pi m kBt. Okay, so for me, what is important is that this is like 1 over square root of t. All right. So again, we know that this, so why is it interesting? Because this guy really controls the crossover from quantum to classical. Okay, so to classical physics. And of course, the classical physics of the gas that I am discussing is very trivial, right? Because I'm just looking at particles, non-interacting particles in a quadratic well. So classically, I mean, they are just described by the Boltzmann weight exponential minus beta x squared over 2. Okay, so these are just Gaussians and full stop. So where this, so the question is how this and when this, when does temperature become relevant either in the bulk or at the edge? Well, basically, you see that in the bulk, that means that in the bulk, if I want to understand this crossover, of course, I need to compare lambda t to L bulk. Okay, if lambda t is much larger than the interparticle distance in the bulk, then basically that means that I have reached in the quantum regime. On the other hand, if lambda t is much smaller than this length in the bulk, then I have essentially the classical physics in the bulk, and the same at the edge. So if I look at this, if I look at this temperature scale, both in the bulk and at the edge, you will see that I will have a different regime of temperature simply because the scaling and the interparticle distance either in the bulk or at the edge have a different scaling with n. So let's try to be more concrete. So if I look at in the bulk, this crossover happens basically when lambda t is of order of L bulk. And that means that this is when 1 over square root of t is of the order of 1 over square root of n. So that means that when t is of order n. So that means that if t is less than n in the bulk, well, I will observe the Wigner semicircle essentially. Then if t is much larger than n, then I will just observe the exponential, the Gaussian, right? Exponential minus beta x squared over 2. And you can even describe the full crossover in details. This we have done, but I will not discuss this too much. Now, on the other hand, at the edge, I can just do the same, right? So the crossover occurs for lambda t, which is of the order of L edge this time. And so that means what? That means instead that now t is of order n to the power 1/3. Okay? So I should say, because we are physicists, that should be written as kBt of order h bar omega times n to the 1/3, of course. But what is interesting is that n to the 1/3, of course, is much less than n. So what is nice is that if you are in this regime, that's what it means. If you are in this regime, so typically, so if we set t of to be of the order of, it's capital O actually, it should be it's not a small o. Let me be more. Well, that means that since we are in this regime, n to the 1/3 much less than n, then basically the bulk will not be affected. And that means that if you look at what happens in the bulk, you will see the Wigner semicircle. Okay, so if you look at the density in this regime, the density will be given by the Wigner semicircle. Just do it in blue. That will be Wigner. But on the other hand, if you look at the edge, okay. Well, because of this argument, it's not a proof, but because of this argument, you might expect that things will be different, okay? Or at least this should be the regime of crossover at the edge between a kind of classical behavior and a quantum one, okay? But the rest of the bulk itself will not be changed, and this turns out to be the very nice. I mean, it turns out to be a nice, quite nice scaling regime, and that's what I want to discuss with you now. I mean, and I will conclude basically this will end up our excursion
The behavior
in
is just
fermions.
Gaussian. Eh?
Sorry?
The classical behavior is just Gaussian.
Yeah, the classical behavior is just Gaussian because indeed the Boltzmann weight, so V of x indeed is quadratic. And that means that you will get exactly exponential minus beta v squared, beta x squared by 2. Okay, so indeed you will get this this guy. Yeah, precisely. Okay, so in order to describe this limit here, I will set a parameter. So I will call basically t. I will just denote it as 1 over b times n to the power 1/3. So you might think of b as an inverse temperature. Okay. Now, if you look at what happens there, you can actually compute the, so the question is, what happens to the airy kernel there? Okay, is there any deformation? Is there any interesting things that happen? It should be, but how will be this airy kernel that we have seen before? How will it be modified? How will it get modified? Well, in fact, one can almost guess how it will be modified from this formula here. Okay, because this should essentially converge to the airy kernel, and we should have basically now the airy kernel, but weighted by the Fermi factor. Okay, you can more or less guess what it should be. Of course, this has to be.
New question actually. So if I
Yes.
take strictly large n limit, n infinity limit, this kernel has like this delta singularity, right? Because of the completeness of this pi functions.
Well, you see, you have the Fermi factor here, right? So this.
You said that if I'm sending n to infinity, mu is also going to infinity by that singularity.
Yeah, if you really do the naive, yes. So that's the very naive way of doing the large n limit, yes. But this is not the real interesting one. I mean, so you have to take care because your mu basically also gets large. So you will not get this delta actually that you are saying. Okay, you cannot do that.
So this 1 over n corrections also are the most
Yeah,
important.
exactly. So in fact, at the edge, this becomes quite, quite non-analytic. I mean, the perturbation, the 1 over n expansion doesn't work. I mean, what I'm saying is that you really need to work in what is called a double scaling limit if you want.
Okay.
And that means that you need to resum a certain part of this perturbation theory to get something non-trivial.
Okay, thanks.
Okay. And so let me just tell you what this kernel now becomes. So if you look at now K mu,
Gregory,
yes.
So when the temperature is between these two temperatures, into 1/3 and order n,
Yeah.
between larger than that and smaller than n. So at the edge you would see a Gaussian behavior, whereas in the bulk you would see inner
Yeah, essentially, yes.
And you know the connecting function between these two functions.
Yeah, this is okay. This regime actually has not been studied in detail. I mean, it looks like a rather tricky regime. Maybe I will comment on that in a minute. Yeah, that's an interesting crossover regime between the two at the edge, which has not been really discussed. I will say, like, I can say things a bit qualitatively, but beyond that, it's pretty difficult. So it's a non-trivial question, actually. As far as I know, it has not been studied in detail.
Okay, thank you.
So I have, say, x edge here and minus x edge there. So what I want, so the scaling form that you get when you look at this guy now, so if you take the large n limit with the scaling there, so it converges to a scaling form, which is very similar to what we have seen before. So we have this 1 over wn, which is always the same. And then we have a new, let me call it kb, of, okay, again, the same. So x minus x edge divided by wn, y minus y edge divided by wn. And this kb actually has I will just write it for you. So it's an integral over the whole real axis now, and it has this form. So this is very similar, sorry, to what we have seen before. But now, of course, you will have the trace of this Fermi factor, which once things are set up properly is simply that. Okay, so you can check. So again, this has to be compared with this. So this is a deformed Airy kernel. Okay, so this should be compared with the one that we had at 0 temperature, which was just this one. Okay, which was this guy. Okay, so this guy, you see, you have the product of Airy function and times 1, but this is not exactly 1. This is more an indicator function on R plus. Okay, because you see that here the integral goes from 0 to plus infinity, while here, of course, it goes from minus infinity to plus infinity, but with this beta factor. And indeed, you can easily check that when t goes to 0, that means when b goes to infinity, it means that this becomes huge when u is negative. And therefore, when u is negative, so when b goes to infinity, what happens is that these integrals here does not range from minus infinity to plus infinity, but instead from 0 to plus infinity. Okay, so that's just the way to see how this deformed Airy kernel becomes the standard Airy kernel at 0 temperature. Okay. So now, once you have that, then you can compute many things. I mean, again, so now you can say it's let's assume now that this is a good this is also a good description of what happens in the canonical ensemble. That means that let's assume that I can use this kernel to compute what happens at the edge of the canonical, I mean, of the fermions and of the canonical ensemble, and then, for instance, ask about the statistics of the largest, the rightmost fermion. Okay. So I will just use a couple of slides, which I already have, just to conclude with that, and show you a very nice connection, as I promised already, a very nice connection with KPZ again. And this is here. Okay. So this is what I was telling, right? So I am back now to this problem, and I'm in this scale. And I want to say something about the distribution of the position of this rightmost fermion. Now, from the theory of determinantal point process, I immediately have that that this cumulative distribution, which I can interpret as a whole probability, will be given by a Fredholm determinant. Okay, this is this Fredholm determinant. But now, instead of having a Fredholm determinant constructed with simply the Airy kernel, which this is the one that I had before, I have now this K edge. Okay, this is the KB that I used before. I'm sorry about the different notation, but this is KB. And this is this guy. Okay, so this is precisely the deformed Airy kernel. So it's quite nice actually, because you see it's a finite temperature generalization of the Tracy rhythm distribution, and in principle, it could even be measured in experiment. Who knows? So this is something that we are trying to discuss with experimentalists. But from the theoretical point of view, it turns out that there is more with that, and it turns out that there is a very nice connection between this and the KPZ equation. And to see that, let me just come back to the KPZ equation. And for that, I will need to work, or I want to work in the curved geometry. So you remember this equation. So this is typically the setup that I have, and this is taken from this paper by Takeyoshi, Sasamoto, and Spohn and others. These experiments on liquid crystals, okay? And they basically they look at the radial geometry, where they are looking at the expansion of this droplet, and they measure x as a function of t. And it's believed that this model is in the KPZ universality class, in the Cardar-Parisi-Zhang universality class, and this is governed. This should be governed by this equation that we have encountered already in the previous lecture, not the last one, but the one before. Now, this model, as I had already said, can be actually solved. So it had been solved already in the large time limit already for quite some time, but it can be solved exactly for any time t. Okay, and this was done by several groups that I mentioned here, more or less at the same time, both physicists and mathematicians. The names are here, and the result is that, okay, it can be formulated in various ways, but there is one way of solving this problem, which at the end is quite similar to what we have shown here, is that, and this was done actually in particular in the paper by Le Dussal, Calabrese, and Rousseau. So let's look at this crazy object here. Okay, so you might this might look a little bit ugly to you, but it's a kind of generating function. Okay, it's the generating function of this object of exponential of h. Okay, maybe I can just so exponential of h. Okay, might okay, Pierre, I've seen your question. I will come to it afterwards. This exponential of h might be a little bit bizarre, but for those of you who know a little bit KPZ, the exponential of h, you know that KPZ actually is related to the directed polymer, and basically exponential of h is the partition function of this polymer when you do the mapping between the KPZ equation and so nevertheless, this is some object. There is some object, and you want now to compute the generating function of this guy. So what these people, what these smart people have shown, I mean, is that this generating function, you can write it as this. Okay. And if you look at this guy here, so that's a Fredholm determinant with this kernel. And if you look a bit at this kernel, well, you see that it's exactly the same as the one that we had for fermions, except that instead of having b, now we have time here. Okay, so t to the 1/3. So again, in the large time limit, you get the Tracy-Rhythm distribution, but for finite time, you will get some kind of deformation. But this deformation turns out to be exactly the one that you would get for the fermions. Okay, so this is what we had for fermions. This is just the formula that I showed to you, but for fermions. And if you just look at the one for KPZ, well, you see that they are exactly similar with this identification. Okay, so that's quite remarkable. And unfortunately, at the moment, no one really understands why there is this connection. But basically, 1 over the temperature is actually like time to the 1/3. Okay, so high temperature is like high temperature in the high temperature in the fermion problem is like short time in the KPZ equation. And this has actually allowed us to obtain some short time expansion and large deviations computations for this problem. Well, you can go a bit beyond that, but so there is a probabilistic interpretation between this identity beyond the formula, but maybe I can take question. So okay, I maybe someone wants to ask a question, but there are already 2 questions in the chat, so maybe I will just. So Pierre Merny is asking, for large temperature, can one get Weibull fluctuations close to the edge directly from the expression of the kernel? Yes, so actually it turns out that it's not, okay, it's not Weibull, but it's another, so you have in mind a connection to the extreme statistics of IID. And in this case, it's not Weibull, but instead it's a Gumbel distribution. And you can actually show that this distribution here, but it's not apparent on the formula, but is actually a crossover from the Tracy-Rhythm distribution to the Gumbel, so at high temperature. Okay, there is even a paper by Kurt Johansson which is called From Gumbel to Tracy-Rhythm, where he actually analyzes that. So in the limit of 0 temperature, you will get Tracy-Rhythm. So that means B goes to infinity. And when B goes to 0, instead, you get the Gumbel. But it's quite, it's not really apparent on that. And one of the reasons why it's not apparent is that, of course, to get the Gumbel, you need to make some nice, I mean, clever rescaling. You need to look at the correct variable. But this is true indeed, yeah. So I hope, yeah, directly on the kernel, you cannot see that. I think you really need to look at the Fredholm determinant to be complete. So there is another question. How do these edge scaling functions look? Do the asymptotes have some well-known forms like exponential or power law? Yes, so typically they are stretched exponential or exponentials. Yeah, one thing that I can show you, I mean, for instance, for the kernel, is there something that I can show you here? Let me say, yes, probably that. Yes, okay. So this is something that I can show you. So from the kernel, actually, you can get the density. Okay, so that means that this is the Wigner semicircle that I discussed. Now, if you look at really what happens here, you should see the deformation of the edge profile at finite temperature. And basically, it has this shape, which you can, so this is just the diagonal part of the kernel. Okay, so that's this guy that we have seen before, but evaluated at the same point. Okay, just to make life a little bit easier to plot things. So it has this shape here. So this is the zero temperature case. Okay, so zero temperature, what you see is that there are some oscillations here, and of course on that side they need to connect to the Wigner semicircle here. So there is a square root singularity, and on the left side actually it decays very rapidly. It decays like a stretched exponential in this case. Now at finite temperature, this is what you get. These are the curves that you get at finite temperature. So things are a little bit different. Well, first you see that the higher the temperature and the smaller the oscillations. This is somewhat expected. These oscillations are related to some interference effects, and they are damped, more and more damped as temperature gets high, and eventually you see that at some temperature it's hardly visible. They are there, of course. If you really look close at them, you will see some oscillations. The Airy function has these oscillations, but they are strongly damped. It still goes like square root on that side, so it's algebraic because it has to connect again to the Wigner semicircle. But on the other hand, on the other side, it actually decays much slower. Okay, so here it's exponential minus x to the power 3 by 2, and it becomes only exponential on that side, exponential of minus x. And the reason, of course, is that we know that eventually at finite temperature, really at high temperature, the density will have a support on the whole real line. Okay, so that starts to be seen already here with this exponential decay. And then you can analyze in details. Well, you can do some asymptotics analysis of various quantities. Of course, this is not so easy in general. I mean, the asymptotic analysis becomes quite complicated, but it's doable. Yeah, so that's.
Hey, Gregory, I had one question.
Yes.
So when you say that the results that you showed for the peer and that was for the finite time, but still large, right?
This is actually true. Okay, this is large, but compared to a very, very microscopic time, so that you don't see, because they put this, as you said the other day, they put this wedge initial condition, but immediately after, it's. I mean, you don't see it. So it's even valid at really a very short time, but slightly bigger than this artificial scale that you have to put. But it's valid for microscopic time in principle. I mean,
so the reason I asked the question, what I remember, they had some formula which was like a generating function for arbitrary times, right? And
yes, yeah. So that's the one basically.
Okay, and from there, so the results related to the short time for the Babuk and others that come from.
Yeah. So that's the one. Okay, the first that we derived the short time. I mean, we derived it from that formula. Yes, exactly. Yeah.
Okay. And
we derived it.
Okay.
Yeah, we derived it by analyzing, in fact, this Fredholm determinant, precisely this guy.
I see.
at a short time. Yes. Yeah.
Other question is this: when you look at this directed polymer problem through this, so then even there you have the determinantal point process representation, or does it emerge also there?
So what do you mean exactly?
So I mean, when you look for the Z, so that's what
yeah.
Hofkohl variable, and
yes, exactly. This exponential of h is Z. Yes. Yes.
Yeah. So in that problem, when you look for their generating function, you get like, so this Fredholm determinant form that you get. So for their correlation, you also could write in terms of determinants.
Yeah, absolutely. Yeah. In fact, I mean, in their paper, I mean, Le Dussal and even, I mean, Le Dussal, Calabrese also, and also to some extent, Spon, Sasamoto. I mean, they actually look at the polymer directed polymer model, which they can map to this Liebling-Niger model, which they eventually solve using better ansatz.
Yeah.
Yeah.
Okay.
So yeah, you have exactly this structure.
Okay, thanks.
Yeah. What are actually these oscillations which go away with temperature? Well, I mean, it's I mean, as I said, I mean, these oscillations. Okay. They actually quite very they are very clear. So let me come back to this picture. I mean, loosely speaking, I mean, usually the oscillations that you see in quantum mechanics, they are really due to the wave nature of quantum mechanics, and typically they are due to interferences phenomena. And you expect that at high temperature, where you kill the quantum effects, basically you also kill these oscillations. But there is a more precise things to say here, more physical. I'm sorry, I just want to find the right plots to show you. Yes. So okay, nice. So what are these bumps? Let's look at zero temperature. I think it's quite interesting to look at that. This is the zero temperature case, okay? So actually what you see is that this is basically the typical position of the rightmost fermions. This is the typical positions to the second rightmost, the third rightmost, etc. So for instance, if you really, if you would really plot the distribution of the rightmost fermion, which is in this case Tracy-Widom, well, you would really get something like that, right? You would really get something like this. That's the first guy, etc., etc. So that means that what the bumps that you see here correspond somehow to the typical positions of these ordered fermions. Now it turns out that when you start to increase the temperature, of course, the rigidity that we know in quantum mechanics, this is the rigidity that I was talking about also in random matrices. This rigidity that this kind of regularity, the fact that the typical positions are quite somewhat frozen. When you higher the temperature, well, they tend, so this will tend to be larger and larger, and somewhat these oscillations at some point will be less and less visible. So you can see still here the position maybe of the first guys, the second guys, etc. But as temperature gets higher and higher, this of course tends to disappear, and that's why these oscillations eventually disappear in this precise situation here. Is that clear?
Are these oscillations extended inside the bulk as well? I mean, towards the left of this?
Yeah, but also when you go into the left, also what happens is that they also get damped. So that means that the higher you go in that direction, and the less visible they become. So the amplitude is also damped when you enter into the bulk. So in fact, for finite end, they are visible. So in fact, for instance, if you really plot maybe you have seen these plots, but if you really look at the density for finite n, you will not see really the Wigner semicircle, but you will see a kind of, so for instance, okay, I'm just doing this so that's the Wigner semicircle. And what you will see if you really take your computer, you will see some oscillation around that. So yes, for finite n, you will always see oscillations, but in some region of space, like in the bulk, they tend to disappear in the large n limit, and it's only in the 1/n corrections, for instance, that you will see them.
Okay.
Is it clear?
Yeah.
Okay.
I had one question.
Yes.
So for this Wigner semicircle,
Right.
how does the diameter like increase with temperature?
Okay. So that's okay. So basically, what happens is that in this regime of temperature that I was considering, so this one, the bulk is not affected at all. That means that the diameter will not change. Okay. Things might change a little bit when you go to temperature that are of order n itself. Okay, so if you really want to perturb this, you would really need to so that means the support. You will really need to go to t of order n, and when t is of order n, essentially what happens is that the density becomes extended over the whole axis. So I don't know, maybe I'm sorry, I'm into scrolling down like this, but maybe I can show you what it gives. If
At very high temperature, like temperature like greater than n, it should go
yes,
to this Gaussian form.
yeah, exactly. So yeah, so that's what you would expect. What you would expect to have a crossover between these two guys.
Yes.
Okay. So one is so this is the t equals 0, and this is the large T. I mean, t goes to infinity is a bit extreme, but you will get the Boltzmann-Gibbs measure. So question is, how do you interpolate between these two, right?
Yes, because here you have like a support over finite region, whereas in
Yeah.
the Gaussian it's extended.
Yeah, exactly. So in fact, okay, I can show you this because so it becomes I have a plot actually of how it looks like. Yes. So it goes like that, right? So this is the t-axis. Okay, and this is z is x actually. Okay, so here you have the zero temperature of Wigner. So you see that in these scales, as soon as t over n is finite, you immediately have an infinite support. Okay. So you have a crossover, if you want, from the Gaussian here to the Wigner there.
Oh, but the crossover function that connects these two regions, that's probably not known, is it?
Yeah, the crossover that connects these two, basically, okay, in this regime, this is this Li half function. Now you are really asking on how this, I mean, what happens really, okay, this maybe has not been really studied in detail indeed. Because again, in this regime where you take n over t fixed, okay, so that's the variable y, you immediately have an infinite support, except at y equals to 0. So you're asking about the y goes to 0 limit. Yeah, this is probably a regime that has not been. But again, as soon as you are slightly above n, so that's the regime, right? T over the n h bar omega. Okay.
Okay, thank you.
Sorry, Gregory, I just had
Yes.
one question.
Please.
If you think about the Dyson's log gas, classical Dyson's log gas, there also when T goes as N, you have this crossover, right? But there the reason is entropy, right?
That's true. Yeah.
And in that sense, is this? But here the reason is, as you said, some de Broglie wavelength and so on, right? So is
Yeah,
there
I
a
think.
connection in this
Okay.
interpretation, or?
Yeah, that's interesting. So what Manas is saying is that if you look at the density in the matrix model this time, and if you take beta, which is 2 for GOE, 1 for GOE, Now, if you say, okay, let's look at what happens when beta is very small, and typically when beta is of order 1/n, there is a very nice phenomenon that occurs, which is that you lose the Wigner semicircle, and it's more than that, is that the density itself ceases to have a finite support, and the density becomes spread out over the whole real axis. And the reason for that is that when you do the Coulomb gas approach, you need to include a term which is due to entropy, which becomes important. Yeah, that's a good question. So the mechanism, I think, are rather different. The form, of course, of the profiles are quite different. I don't think that people have thought about that. I mean, whether there is a way to connect these two. Yeah, that's an interesting point. Yeah.
Isn't that the contribution of the entropy in these two cases, in the fermion and in the log gas, are different? In the fermion cases, you have this statistics, Fermi statistics,
Yeah,
but in the log
definitely.
gas, so the contribution of the entropies are different
Probably.
at finite
Yeah.
temperature.
Probably. Yeah.
So
I
at
guess
finite
so.
temperature, these two models may not be.
They may be rather different. Yeah.
Different.
Yeah.
So also, of course, in the extreme high temperature and extreme low temperature, they match. But in the intermediate temperature, this Li half function is for the Dyson's log gas, it is different, right?
Yeah. It is. Yeah.
So okay.
Yeah. It's given by some, I think, by some spherical functions, D functions. So anyway, yeah. But that's yeah.
I see. Thanks.
Other questions? Okay. So maybe in the time which is left, I just want to maybe I would like to touch upon a new subject, and maybe I will just introduce it. It's yet another subject, but which is deeply connected to everything that we have heard about until now: random matrices, fermions, and also KPZ to some extent. And this has to do. So let me just come back to the main outline. Sorry. So this has to do with non-intersecting path. Okay. So I will just briefly introduce the subject today, and probably I will just show you some nice picture, and maybe explain qualitatively why we are interested in this kind of models. So yeah. Okay, so let's so that was this fourth lecture. I will just keep it in this one, so that we can have it all together. Okay, so that's the third part. And the goal would be to introduce you to Dyson's Brownian motion, which is a kind of dynamical version, if you want, of random matrix theory. Oops, sorry. Of random matrix theory. So the basic model that I want to study is the setup is the following. Okay, so I will just, so let's look at okay, I want to have this like this just to set up. Oops, sorry. Okay, so that will be basically time, and these are positions. And I want to study, I mean, a new object. Somehow I've not yet really discussed too much dynamics, but let's look at a Brownian motion. Okay, so I will look at. Oops, sorry, I'm starting to be tired. So I would like to consider, say, in the simplest setting, a Brownian motion that starts at A and ends at B. Okay, so for me, Brownian motion, I mean, I know that you have heard a lot about Brownian motion during the first week with Hugo. So that's how I want to think about Brownian motion. Okay, so so at the moment, of course, the things are not directly connected to what I've said before, but I want to tell you, to present you one setting where you could feel a bit the connection. Okay, so it starts at time 0 and then and ends at time t, and this zeta of t is just, for me, I mean, this will just be a delta correlated white noise, and of course it has 0 mean. Okay, so many things can be studied about, of course, about this guy. Now, a situation that I want to study in details is the following, where I don't have, it's not that I have only a single Brownian motion, but I want to consider the case where typically I may have a collection of them which are independent, except that they cannot cross. Okay, so they may start at A1, A2, A3, say A4, for instance. They will end up at B1, B2, B3, and B4. So again, non-intersecting Brownian motions. So they are independent again, but the only thing that I impose on them is that they cannot cross. Okay. So you can already see that there is some, I mean, qualitative similarities. I mean, in the sense that this non-intersecting condition is a bit similar. So that means that they don't want to touch themselves, each other. So they behave in a way like fermions, and I hope I will be able to make this idea a bit more quantitative next time. It turns out that in some cases, they also look very similar and are very similar to random matrices. And this is the case of precisely the case of Dyson's Brownian motion that I will arrive to at the end. So it turns out that these models, before they sort of became interesting to a large community of physicists, in particular in the context of this KPZ and people interested in random matrices. These models actually were studied a long time back, and in fact, in physics, they were first introduced by De Gennes in this very nice paper, actually from March '68, where he was studying these kind of fibrous structured polymers. And you see, he really has this structure that very similar to the one that I depicted. He has these lines here that are attached to these plates. So they are essentially fixed for him. And again, so these are like elastic line. This is a sort of simple model of polymer. And this elastic line, actually, you can thought of it as a trajectory of a Brownian motion. And the condition that he actually imposes on them, the constraint, say, is that these guys actually cannot cross. Okay, and so there had been quite a few work. I mean, some interest around these questions, and after the paper by De Gennes, this became even more popular after a very famous paper by Michael Fisher in the 80s, where he was studying these non-intersecting walks and Brownian motions in the context of melting transitions, wetting transitions. And there are there are quite a few papers, huge amount actually of papers around this topic by Michael Fisher himself, Fisher Hughes, and many other people have worked on that. Now, even more recently, people actually have been able to look at this kind of vicinal surfaces. So that you just create them in a quite easy way. So this is the result of a simulation. So this was done in the Maryland group, in particular, in the group of Ted Einstein. So basically, you take a crystal and you cut it along these lines here, and what you see then is that you have some terraces that are formed. Okay, and you see these lines here, and if you look at them from the top, you see this very nice structure here, and you see this sort of rough lines here, which by construction do not intersect, and this has also triggered a lot of activities in the context of fluctuating interfaces. Another set of problems where people have been interested in these models is closer somehow to combinatorics and mathematics. And okay, I just quoted one of these papers. So one type of configurations that are quite interesting is the case where all the walkers here essentially start from the same point. Okay, so the initial and the end point are very close to each other, and the trajectories, when you add many of them, again you insist on having them not to cross. You see they form this kind of watermelon type of configuration. Okay, so that's why people name them this watermelon configuration, and this has generated a lot of activities in the context of combinatorics. There are many famous papers on this. This one is actually about the generation, how to generate these kind of things. This is a question that we recently worked on, by the way, with Satya and our student Benjamin De Bruyne, but I will not have time to cover that. But nevertheless, that gives me the opportunity just to mention that more recently, I'll say already in the context of the Kardar-Parisi-Zhang equation, people actually have studied a lot this kind of watermelon configuration, and I will end up with that just to give you one more motivation. Is I will not have time really to show you this in detail, so I mention it right now, but I can already tell you that there is a beautiful connection with KPZ, which we just have seen. That serves here as a motivation, I hope, because I will next time I will show you how one can really study this kind of configuration using fermionic approach, and using this fermionic approach we will show a nice connection with random matrices. But let me just tell you that indeed, if you look at this very specific configuration where you have these watermelons, okay, so I'll just say look at them this way. So if I look at this type of Brownian motions like that, and okay, so what I want to say is that okay, so I will basically I want to have them. So I start at say at 0 and I arrive at 1, and I want to consider n vicious walkers and what vicious walks. So okay, these non-intersecting Brownian motion, sorry, they are sometimes called vicious because you have to imagine that if they touch each other, they kill each other. Okay, so that's Michael Fisher actually introduced this notion. So they are vicious in that sense. So if I look at these n vicious walkers, in the limit of large n, and in particular, I want to look at these watermelons configurations. Well, they were actually studied a lot in the context. They were initially introduced, as far as I know, in the context of KPZ by Spohn and Prehofer. Now, if you look at these guys, you see in the large n limit, what will happen is that, well, if I look at the top curve, well, it will have essentially a kind of deterministic shape. Okay, the fluctuations will tend to be very small. And I hope I can show you this next time. But let's see now if I want to zoom on the fluctuations of this guy. So what will happen is that, okay, if you have n vicious walkers, typically the extension here will be proportional to square root of n. And at the order of square root of n, everything looks deterministic. But you want to look at fluctuations. Now, if you zoom in, say in the center, close to half, and if you start to zoom in on a window, okay, the size is not very, so this should be, this one will be of, if you zoom in at, so this should be of order n to the power minus 1/6, and this one actually should be of the order n to the power minus 1/3. So the format of my rectangle is not correct, but anyway, the nice, I mean, and very interesting thing is that if you look at the top path, so you see how it looks like, right? I mean, you have to imagine. It turns out that on this scale, what you will see is that the behavior of this line around the blue one, so the black one, if you really subtract the deterministic part and look at the fluctuations on the scales that I have indicated, then what you will find is that it is exactly described by kpz in the limit of large n in the curved geometry. So in other words, if you zoom at what happens here on the large n limit, it should basically look exactly as this type of kpz interface that I showed you before. So exactly of that kind. Okay, so it's not completely trivial to see, of course, but as you can imagine, this has triggered a lot of interest because this is a theorem. This means that one can approach kpz, the kpz equation, by studying this kind of configuration here, and then taking the large n limit in a correct window and have access to the non-trivial properties of kpz. So that's also why, I mean, this kind of models have been introduced, and maybe there is a model actually which is attached to that, which is the so-called PNG model, polynuclear growth model, which is in the kpz universality class, and which can be reformulated in terms of these non-intersecting lines. So I will stop here. So just to tell you that, okay, so next time I will show you how to treat and how one can handle and make computations with this kind of non-intersecting lines. So I would like to show you what is explained to you, what is known under the name of the Carlin-MacGregor formula, and then show you how one can interpret this formula in terms of fermions. Since okay, we are already a bit familiar with fermions, that should be a good application to it. And I hope this, yeah, the hope of that was the motivation. I mean, trying to show you some motivation for the study of these guys. And then I will show you what is known as Dyson's Brownian motion, which is again a dynamical version of random matrix theory. So I guess I will end up here.
Okay. Gregory, I have a question. Yeah. See, mathematically, I understand the difference between this vicious walker and this walker which doesn't cross each other, basically with a hardcore interaction, and basically just in terms of the boundary kind of boundary condition you put in the focal
Yes,
point.
exactly. Yeah.
Yeah, but physically, I mean, why are they so different? In one case, also, I mean, if you just think of like a point particle, in one case they can touch each other, but they cannot cross, and here, I mean, they can go infinitesimally close to each other, but they do not touch. I mean, why do? And in one case, I guess you just get gumball, right? For the
yeah. Well, so I think that it's a bit. You're right. I mean, one way of thinking about it somehow is that.
Is it the ensemble basically you are taking where you just
precisely.
The path where they,
but precisely, I think that's the way to think of. I mean, it's better to think in terms of Dyson's Brownian motion in the sense that these particles actually, in some very special cases, it's like non-intersecting Brownian motion, but they actually interacting. I mean, they have this log. I mean, this is a log gas, right? So they do interact via this 1/xi minus xj interactions. It turns out that there is a very special point, which is beta equals 2 again, where this is like. It turns out that for some reason this is equivalent to non-intersecting path, but really, I mean, I think it's somewhat more.
Yeah, like if you think of it like an experimental system, I mean.
Yeah, but I think it's better to. I mean, one should keep in mind that there is some interactions actually between them, which is not a simple hardcore somehow.
Yeah, I guess. Yeah.
But I agree. It's.
I mean, yeah. I mean, if you don't look at the equations mathematically, it looks like a very small change. But yeah.
Yeah, I agree. Yeah. I see another question in the chat by Jean-François. Yeah, what would be the analog of the finite temperature in the model of vicious walkers? Yeah, that's a very interesting question. I will not have time to cover that, but the analog of a temperature is really would be the fact that you are considering periodic boundary conditions. So that means that instead of having your particles in this setup here, what you really need to think of is that okay, how should I say it? Yeah, this is really like having particles on a cylinder, in fact. So you would really have to imagine that basically. And now you look at basically you look at trajectories which sort of are wrapped around this cylinder. And basically then it's I would need more time to really answer fully your question, but morally this is proportional to 1/1 temperature. Okay, so basically when at 0 temperature, they do not really experience these periodic boundary conditions, but that's the effect of temperature. And in fact, so we have actually we have a paper on that. I mean, which is which is called the periodic Airy process, which is a periodized version of the of this process that describe this Dyson's Brownian motion in the large N limit. Okay, I mean, I didn't discuss enough to explain to you why is it so, but this is the way to think about it. I don't know if it's satisfying, but that gives. Okay.
Gregory, so in the case of the vicious walker with the Brownian bridge condition, so the connection to random matrix, is it the way to see that you will have one, that boundary condition comes from the viciousness and the bridge condition gives you an effective harmonic potential?
Yeah, somehow that's what happens.
And that two together gives you exactly the.
Yeah. So yeah, indeed. So in fact, this connection can be really really done. I mean, very precisely in this setup, in the following sense that if I look at the let me take just another color, but I will show this next time. If I look at these watermelons, and if I now say, okay, let's have a look at the joint distribution at a given time tau. Okay, so if I just do a slice, and if I ask what's the distribution of the position of these guys, then what you can show is that the distribution of these positions is exactly, again, they are exactly distributed like in the GUE ensemble. So that's something that I will show next time, I hope.
Okay. But the length of where your bridge condition is put, that does not come as any parameter in the.
Well, I mean, okay, it comes out as a simple rescaling parameter, indeed, yes. So that's why I put it equal to 1 here.
Okay, so this you will discuss in the next.
Yes, I will discuss that next time. So that will be the basic goal of next time, to show that this is indeed related to RMT. So that will be the goal.
Okay, thanks.
So I guess there's one more question. Okay. Yeah, I guess you can stop here. I guess.
Okay.
Yeah. Maybe I'll just ask you a, I don't know, naive question. This I don't know if it is even makes sense, but okay. So this year, this fermion problem in finite temperature. So at a given temperature, this bulk is more quantum than the edge in some sense. Is it true? Like okay.
Yes.
Okay. So then these oscillations for finite and which disappears at the edge, they still persist in the bulk for longer time, or the oscillations are. I mean, I guess you have to look at in some scale where you see the oscillations, right?
Yeah. So there are two effects somehow that kill the oscillations, right? I mean, there is one which is the fact that you are looking at large n, and the reason for that is that for fermions, for large n, you really look at states which have a higher and higher energy, and they become more and more classical. And of course, you have the effect of temperature.
So suppose I fix both n and temperature, I guess.
In that sense, it's true that the I mean, you really need to yeah, the bulk is more I mean, I prefer to think of the bulk as being more or less sensitive to fluctuations than the edge. You formulate it in a slightly different way. You want to think of the bulk as more quantum than the edge, but I'm not. I usually think of it as by saying that, okay, at the edge, I mean, there are very few particles, and the density is very low, and so you are typically much more sensitive to fluctuations, either thermal or quantum, by the way. And that's why somehow you destroy the quantum effects more easily. But you are right that in principle that's true, that the at this scale, I mean, the quantum oscillations in the bulk are just not affected. I agree.
Okay, I guess we'll see tomorrow.
Okay.
Yeah. Okay.
Okay.
Yeah. Bye bye.
Bye, guys.